Hello class, welcome to today's video on chapter 3.1 Powers and Polynomials. As you're watching the video, please remember to take down important notes, formulas, equations, and theorems. Feel free to pause or rewind as you need to, and feel free to repeat watching the videos as much as you need to. Don't forget to submit your online WISC before class, and we're ready to begin. So chapter 3 starts off, basically chapter 3 is about little rules on differentiation. So it may not have differentiation in the title, but today's video is about differentiating powers and polynomials, which are the easiest to differentiate, and you will really enjoy this section. So let's begin. So let's say I have a function f of x, and it looks, kind of sinusoidal or whatever, but that's not important. But if we take a look at f of x and we look at the slope of the tangent line, let's say it's m. Well, if I multiply that f of x by a factor of 3, that means I stretch it vertically. And that means that the slope at that same point is no longer m, but it's also a stretch vertically of the slope, so it would be 3m. Or if I were to compress the function vertically by a factor of 1/2, as you can see here, that will also affect the slope of the tangent line at that point to be a half of the slope of the tangent lines at the previous point. And then if I were to do two types of transformations, vertically stretch it as well as reflect it by multiplying the function by -2, then that also will affect the slope of the tangent line at that point as well. So ideally, since we're talking about derivatives, which is can be calculated as the slope of a tangent line at a point, then we can come up with an expression to represent how to find the derivative of a multiple of a function. And we call that multiple a constant multiple, and here we use 3, 1/2, and -2. But for this formula, if f is differentiable and c is a constant number, and so the limitation on c is that it just has to be a constant number, so it can be any number, then the derivative of the function c times f of x is equal to c times the derivative of f at x. So basically, we're making a multiple of the derivative, as you can see here. Now the proof of it is based off the proof of the definition of derivative, as you can see here. Limit of, as h approaches 0, of c times f of x plus h minus c times f of x over h. That's basically the same as pulling out c. And then what you're left with is c times the limit of f of x plus h minus f of x over h, which is exactly the definition of a derivative of the function at point x. So this is an important rule to remember, that the derivative of a multiple of a differentiable function is equal to the multiple times the derivative of that function. Let's take a look at another property about derivatives, and we're taking a look at the derivative of sums and differences of functions. So let f and g be differentiable, which means the derivative of the functions exists on its domain. And let's take a look at the sum of the two functions, and we're going to show you that the sum of the derivatives, the derivative of the sum function is equal to the sum of the derivatives. And as you can, and the same here for differences as well. And the proof of that is pretty much straightforward using the definition, limit as h approaches 0. Here we take the sum function and we find a limit as h approaches 0. And we basically do some algebraic combining and grouping, that's what I meant. And as you can see here, we end up with the limit of f. We end up with the definition of the derivative for f at x and the definition of the derivative of g at x. And so that works for not only the sum of two differentiable functions, it also works for the difference of two differentiable functions. And here's the reason why. And the last rule we're going to look at is the power rule, which we already have some experience with, which is if I have a constant real number n, And we already know from previous examples that the derivative of x to the n of the power function is equal to n times x to the n minus 1. And if you don't remember why that works, here we have the definition of derivative. And as you can see here, if I were to expand x plus h to the n, I end up with a whole bunch of terms of x and h in combination. I can divide out h by each of those terms, and I end up with terms involving h squared and powers of h to the right. And so if I just take a look at, after I divide out both h's from each term, I end up with this expression. So as h goes to 0, these expressions will also go to 0 as well. And I'm just left with this. And that's why the derivative of the power function x to the n is equal to n times x to the n minus 1, as we can see. So that's basically all that we're going to do for the video, because you should be able to prove and use the formulas to find the derivative of polynomials. It is, to me, one of the easiest things to do because of the formulas, but you still are responsible for knowing why it works based off the definition of a derivative. So that's it. Very short video. Have a good day.